Good evening, everyone, and welcome to this new webinar organized by the Parisian local chapter of EAG, the European Association of Geoscientists and Engineers. So I'm Sonia Isabella, and I have the pleasure to host this event with my colleague Elias, who will introduce himself later. So let me first say a few words about myself. I am the company relationship lead of this local chapter. My background is more in mechanical engineering and modeling, and I've been working around 10 years in the energy sector. I am currently a founder in residence at Marble, a startup studio based in Paris and specialized in climate techs. Today's webinar is the 7th webinar of the chapter, and it is going to be about carbon capture, utilization, and storage, and more particularly about some current initiatives in the EU. CCUS is a vital option in reducing emissions during the energy transition. And as oil and gas will still remain, at least for a certain time, a significant part of our energy mix, long-term underground storage of their emissions offer a provisional solution to the carbon neutrality challenge, and it will require technological advances spanning over several decades. We're delighted to introduce 3 guests today who will help you navigate through various industrial CCUS projects underway in Europe. Our speakers will provide insights into the intricate process of executing these complex projects, from covering everything from site selection to industrial implementation and operation. So our first speaker will be Fernanda Veloso, CO2 storage expert at BRGM. Our second speaker will be Callum Barrow from Equinor, Subsea Facilities Lead. And our third speaker will be Sonia Isabella López Kovács, a Reservoir Engineer from Repsol. Okay, so before going into the different talks, I wanted to talk a bit about what is EAG. So EAG is a non-profit professional association for geoscientists and engineers, and whose main goal is to promote the development, innovations, and application of geosciences and related engineering subjects. So it was founded in 1951, so it's pretty old right now. And the way it works is actually through memberships. So these memberships, they give you access to a lot of benefits, including the access to a large geosciences database called EarthDoc, to also discounts on various events, courses, education packages, also free webinars, learning resources, and many other advantages. So our main event of the year is actually the EAG Annual Conference and Exhibition, which is one of the largest multidisciplinary geoscience events in the world, with more than 6,000 participants and 200 exhibitors. So next year it's gonna be held in Norway. So feel free to register. And just to tell you a bit more words about what we actually do in the Parisian local chapter. So we are like a team of professionals from different institutions, from different backgrounds, from different nationalities, and we are all volunteers. And we are always looking for new for new partners. So feel free to contact us, either if you want to be an operational member, or if you would be interested in sponsoring us. So to give you a bit more details about the type of events that we are organizing, so this can be in-person events. This can also be online events, and it's most of the time around the fields of geosciences, but sometimes not only. As for example, our first event this year was about diversity in the workplace, and it was organized in collaboration with SPE and hosted by Technip. Then we covered very different topics. Would that be about AI seismic interpretation, or CCUS, but more focused on technologies, or geothermal, as we had 2 events during the spring, one online and one hosted by SLB in person around June. We have some other events that are also going to happen by the end of the year. I will come to that later. But if you want to meet us, I would advise you to come at the GET 2023 conference and exhibition that is going to be held from the 14th of November to the 17th. And we will have a meet and greet from 10:45 to 11 on the 16th of November. Our next event is also going to be about a topic that is not purely technical this time. It will be about how to navigate career challenges and opportunity of the energy transitions. And one of the organizers is actually a former EAG member from our local chapter in Paris, so Lucia Levato. So it's a free webinar again, and it will give you an introduction of the larger program that she and her peers are going to organize in the coming months. So save the date and join us. Now, we also try to collaborate more and more with the different chapters in Europe, and there are also other chapters outside of Europe, actually. So we would like to invite you to attend to the next German event that is going to be a hybrid event on the 28th of November, and it will be about the potential of ground penetrating radar full waveform inversion for hydrogeological application. So it will be of course in Germany. You can attend to it online if you want. Some more details will be provided soon. Now we're finally back to our agenda. So our first speaker, as I said before, is going to be Fernanda Veloso, and her talk will be about CO2 geological pilots in strategic territories. This will be followed by a Q&A session, and then we will have our two other speakers. So first, it will be Sonia Isabella López Kovács from Repsol, who will talk about CO2 geological storage site selection, reservoir characterization, and assessment. And then we will have our last speaker, Callum Barrow from Equinor, who will present to us an overview of the design and operation of the Northern Endurance Partnership project Subsea Injection. And then we will have our last Q&A session, and it will be followed by our conclusions and comments on these talks. Okay, so Fernanda, really happy to have you with us. So I will introduce you briefly. So Fernanda is a CCUS project lead at BRGM, which is the French Geological Survey. She is currently coordinating a project called Pilot Strategy Project, EU Horizon 2020 project, and it is about the characterization and the pre-FEED studies of CO2 storage plants. So Fernanda is a CO2 storage expert. So she's particularly experienced in everything related to site characterization, to safety of storage, to reservoir simulation, and to CO2 injection. And she's a reservoir geologist by background.
What built from a strategy CCUS is another 2020 project, a previous project before pilot strategy. And strategy CCUS, we built CCUS economic plans based on technical, economical, environmental, social aspects of the CCUS chain in eight European regions, 2 regions in France. And from these 8 regions, we select 5 of them to continue working in pilot strategy, CCUS, and focus on the storage part. Pilot strategy is a 5-year project. We have a 10 million euros of the budget and 16 partners, plus 3 third parties, French third parties. Pilot strategy is the objective and the project is to study in detail deep saline aquifers for CO2 storage, The idea is to develop economic evaluation class 4 of the CCS concept for the storage site in 3 regions, France, Portugal, and Spain, and to propose the pre-investment proposal for these 3 sites. And also we have 2 more regions that we are studying in Poland and Greece, where the maturity is not so high than in France, Portugal, and Spain. And the proposition in pilot strategy is to increase the maturity and confidence of these both sites in Poland and Greece. So we adopted a multi-criteria approach where we have the objective of the project, and we will use technical evaluation, environmental risk, societal aspects to make the economic evaluation, socioeconomic evaluation, and include legal framework and incentives to arrive in to establish an economic evaluation class 4 for these 3 sites in Europe. So let's talk about France, what you are doing in France. You are studying, I think I jumped one slide. Yes, here, sorry. The CCS pilot concept in France is located closer to Paris at more or less 100 kilometers from southeast of Paris. So the project is focused in a fertilizer plant where we can store more than 300 kilotons of CO2 per year. The CO2 is already captured for the fertilizer plant process. And for those who knows more about the France geography, the fertilizer plant is here, Paris is here. We are in between of hydrocarbon concessions. The reservoir, the study area, is the Dogar Reservoir. This reservoir is very intensively exploited and studied in France for geothermal, for oil gas exploration. We have a lot of dynamic data. We have coarse petrophysical data from oil studies, hydrocarbon studies. And in pilot strategy, we are acquiring new data, new knowledge. We did a 3D seismic campaign last year. We are acquiring geochemical experimental data from samples, and we did some geomechanical tests. And the area we had a lot of data available, and now we are also producing new data related to CO2 storage. So here, just an example of 2 seismic surface from the 3D seismic block. So we have at the top of the reservoir and the base of the reservoir from seismic. We have the CCS concept that we are studying, we are developing, and the pilot design. So the CCS concept is to store CO2 from the fertilizer plant, to transport it to using new pipeline, maybe trucks, but it's not the best option, because we are doing some work related to societal engagement of local population. We're in the project, and trucks is not the best way. It's not the best transport mode from the citizen's view. We are also now studying the wellbore design, where we put the well location, the equipment, the profile. We need to determine if the well is a appraisal well, and then we can use as injector well. We are delimiting the storage complex and the storage site. The storage site is the reservoir, and we can include the primary cap rock and the storage site. But for the monitoring purpose and for the safety of the storage, we need to define the storage complex. Is the surround area and also the underlying formation until the ultimate cap rock. Pilot strategy, we are also doing risk registers and likelihood calculation using qualitative and quantitative approach to do the risk assessment. We have a technical risk related to the storage, and also we include in this risk framework stakeholders consultation to take into account what stakeholders perceive as a risk. A very important part of the project is related to societal participation and engagement in the project. So we have a trans and interdisciplinary dialogue within the consortium, because we are a multidisciplinary team. We're social scientists, engineers, geologists. So we need to dialogue together, and everyone needs to understand that we want to say. And also we have all work related to the local population in the study area. So we started with analysis of European and national policy alignment, the existing policies. We did regional profiles based on interviews, meta-analysis, and many other documents available to have this kind of regional profiles. So we did this profile for all regions, every region that we are studying in pilot strategy. And then we start the part of stakeholders engagement. So we have a group of stakeholders, the stakeholders committees. These people participating in technical discussion of the project. We meet twice per year. And the idea is to engage people in the project and to produce recommendations for future engagement pathways. To give you an overview about the survey that we did in France, we can see here we did the same survey in Spain, Portugal, Greece, and Poland. So we have a very good rate of people that are able to accept a CO2 storage site close to their home. As you can see here, we have more than 17% of people that respond that it's okay, it's acceptable to have a storage site close to the home, close to their home. And we also asked about how proud you are if you are contributing to climate change mitigation through storing CO2 storage. And if you add the very proud, and moderate proud, or slightly proud, we have more than 70% of people that would be proud to participate, to contribute to the climate change mitigation actions. In France, the regulatory framework is an advanced stage because we had a past CCUS pilot scale project. We have a relevant industry discussing about CCUS. Now the government launched the CCUS strategy in France. So CCUS has become a major topic of discussions. So the major coverage is increasing related to the CCUS. Is partly perceived by stakeholders as unavoidable mitigation strategy, but we also need to couple with other solutions. We had an overall positive evaluation about CCUS in France. Today, we are working to define more in detail the CCUS pilot concept, the wellbore position, the transport mode, and the scalability of the site. The idea is to start with a research permit and to drill the appraisal well, and this well will become the injector well. During this research permit, the idea is to store 100 kilotons of CO2 during the period of the research permit. We have some challenges in France now. At this moment, they are updating the environmental code. So in France, we need to ask a permit in the mine code. But for injecting CO2, we need an authorization from the environmental code. And also we are looking for the founded schema that is not yet defined. So if you want to found our project, you are welcome. So it's all for me today. I have much more information. You can access the site web and you have access for all deliverables of the project concerning the geoscience work and also the societal science work. Don't hesitate to go to the website and to send me an email if you have a question. I think you have a Q&A question now, because my apologies, I need to leave. I have some children challenge now, but don't hesitate to contact me if you have any question or if you want more information. Thank you.
Thank you, Fernanda. Thank you for such an insightful presentation. And yes, we're gonna have the Q&A now. And in fact, there are already a few questions in the chat. So I think I'll just read the first, and other people, if the others have questions as well, they will ask after that. But I think I'll just read the question, but you can also take a look at it. So the question is for Fernanda, and it says the approach for CCUS is the copy and paste approach for underground gas storage led for 50 years by GDF, Foster-NG, and FP. They have already an important database of targets, and for memory, it takes up to 10 to 15 years to validate the storage. Did you have the opportunity to talk with them?
Yes, thank you, Mark, for your question. We have some difference between the gas storage because we will not recover the gas that we are injecting. It's for permanent storage. And another difference is for natural gas storage, we don't have this complexity about the permit. Yes, we talked with Storengy and GDF, and IFPN are partner of the project. So don't worry, they are part of the project. We are in constant communication with them. But we have some very important difference between natural gas storage and CO2 storage. Natural gas, we are recovering this gas. CO2 storage, we are permanently storing them. And it's inside the environmental legislation in France. So not easy to. But in any way, we are aware about that. And if you have, Mark, any idea how to help us with that, please feel free to contact us and we can talk more in detail. But we don't specify 10 and 15 years. The project is for 5 years, so we can count that we have already 5 years studying the area. More 2 years for the permitting process. So more or less than 10 and 15 years, I hope.
Thank you, Fernanda. And thank you, Mark, for the question. There are actually another 2 questions. The next one is from Olivier Ferlat, and it says, hello, did you look at the pilot experience for CCS by Total in Rus like around 2008?
Yes, but we have a very important difference here is the Total whose pilot was in depleted hydrocarbon field. Here we are studying saline aquifer. So it's a very different assess. But yes, more for the legislation work. But yes, of course, we had a look in the pilot of Total, but the reservoir, the geology is really not the same. And I think we have another question about the main drivers for CCUS project.
Yes, we do.
Yeah, so in France, the case in France, we had two drivers. The one was the emitter. The emitter, by the process, they are already capturing CO2. So today we have pure CO2 available to be stored. No need to install capture. And the second one was the geology. So the emitter is a very good place with very good geology. And this was the main driver to choose this area that we are studying. And in France and Portugal, we had other drivers. For example, in Portugal, we are studying an offshore area because it's a place that have a potential to be scalable and become a very important site for Portugal. And in Spain, we are also onshore, and the geology was the first drive, as well the proximity, how close we are from emitters.
Thank you, Fernanda, for such insightful response. We do not have any more questions here in the chat, but if anyone in the audience would like to pose a question, we still have a few minutes for that. Otherwise, we'll just proceed with the presentation.
Thank you, everyone.
Thank you. Thank you also to Malta, Olivier, and Harry for the questions. So next we'll have our next speaker, which is Sonia Isabella López Kovács. So Sonia will be speaking on CO2 geological storage site selection, but also reservoir characterization and assessment. I'll say a few words about Sonia. Sonia is a petroleum engineer by background with a master's degrees in reservoir management from the Universidad Central de Venezuela, but also has a master's degrees in renewable energies and has working experience. Sonia also has worked as a reservoir engineer and advisor in Repsol in Spain. Her expertise includes business development in reservoir, but also low carbon technology solutions, such as geothermal and carbon storage. So I'll now pass the floor to Sonia.
Okay, thank you very much. Let me to share my screen.
Yes, please go ahead.
Okay, you can see my screen?
Yes, we can.
Okay. Okay, good afternoon, good evening, everyone. Thanks for attending this webinar. Okay, I continue for this part. It's referring for CO2 geological storage, more detail, referring to the site selection, reservoir characterization, and assessment. Okay, the main topics that I will cover is the CO2 storage as part of the CCUS process, CO2 storage potential sites, then the capacity, injectivity containment, and the assessment evaluation. Okay, moving about the CO2 geological storage. As we know, CO2 geological storage is part of the carbon capture and storage process. And as we see here in this picture, the CCUS project includes several processes during the value chain, that is the capture of CO2, then the transportation and following for the storage of the CO2 in the geological formation. Each of these steps sometimes have some process that implies the compression and expansion of the CO2 during this value change, and this maybe causes some pressure and temperature change into the process, and this affects the CO2 phase. As we see here in the right side of the slide, we can see the CO2 pure phase diagram, and we see that the CO2 we can find in different phases, and this will depend on the pressure and temperature. We can see that we can find the CO2 in solid phase, in liquid phase, in dense phase, and supercritical phase. And as we see here, this will depend on temperature and pressure. The ideal condition to be storage the CO2 is in supercritical phase, yes, but this will we can reach this supercritical condition when we are above 2 critical points. These critical points is around 1000 psi and 32 centigrades to temperature. Based on that, when we evaluate or when we do the assessment to CCS project, we need to integrate all the value chains that include the capture, then the transportation and the injection, and then need to include all the pressure changes during these phases, because maybe we can get the CO2 in the capture point or by the meters at the liquid phase. Then when we transport with because there are some things happen, some pressure losses, the CO2 can be changed to gas phase and then goes to the well in gas phase. And this affects our injectivity. Based on that, it's important to have an integrated project and include all the process in this evaluation. Okay, the CO2 geological storage can be applied not only onshore, but of course offshore too, as we see in this sketch. Yes, one of the important things that we need to consider is the emitters. Yes, the CO2 emitter, it's need to be so relative close and not so a big distance, because then affect the process at the project and the feasibility of the CCS project. And of course, we need to have a good geological formation to be storage this CO2. Yes, about when we talk about the storage sites, basically we heard that it's two main important places. It's the saline formations and depleted oil and gas reservoirs. But of course, we can storage the CO2 in coal seams and basalt formation. But most of the projects right now are focused in saline formation and depleted oil and gas, focus on that. Based on that, there are some advantage and disadvantage of each cases. In the case to saline aquifers, the good thing is that we can storage more amount of CO2 compared with the depleted oil and gas reservoirs. Yes, but of course there are some challenge or some, not limitation, but some challenge that there is less information regarding about the formation. And sometimes we need to drill an appraisal well or exploration well in order to get some information regarding to the petrophysical properties in this saline formation. Then when we talk about the depleted oil and gas reservoir, the good thing is that compared with the saline aquifer, we have information regarding to the reservoir, like petrophysical properties. We know how much oil or gas this reservoir produces, and this fluid that we produce in this reservoir can be replaced by the CO2. We know that the seal and the faults we have very identified because we have the information. The disadvantage in this case in the depleted oil and gas reservoir is that we have wells, existing wells, that these wells can have a route or a way that the CO2 can be migrated. This is one of the main disadvantage about the depleted oil and gas, and another disadvantage is the current reservoir pressure when we start to inject the CO2, because if this pressure are below to the critical point of the CO2, we have another problems that is related to the hydrate formation in the wellbore or near the wellbore area. That this is one of the points that Fernanda mentioned about the LAC project. LAC projects are very depleted, and if we use this reservoir to inject the CO2, we have some challenge regarding to Joule-Thomson effect. That this is the effect that when we inject the CO2 into depleted formations that are below to critical point of CO2. Okay, based on that, when we refer about the geological sites, we need to take in consideration the petrophysical properties or the reservoir properties that we need to have a good porosity, good permeability, good net pay. Then need to have a good capacity about all the volume into the reservoir, that in order to can be a storage all the CO2. Then we need to take or to evaluate the integrity, not only into the wells or the existing wells or legacy wells, but inclusive about the formation, the seals and traps. And we need to consider also the depth, because in the depth, if we are in a depth that we can reach the CO2 as supercritical condition, we prefer, because supercritical condition of CO2 is the best condition to be storage the CO2 underground. Okay. When we referred about the site selection, there are some technical factors that we need to take into consideration, and another criteria factors that is more related to the environmental, infrastructure, legal, public opinion, and economics. That is what Fernanda referred in the previous presentation. No? That is because public opinion, it's really important when, or acceptance in order to continue or to approve all the CCS project. But when we refer about the technical factors, the technical factor is when we evaluate the reservoir site and all related to the amount of CO2 that can be stored and how much can be injected. These technical factors are related to the capacity, injectivity, and containment. Going more detail about each one, we see here that one is the capacity. Capacity is referring about how much CO2 can be stored inside the reservoir. This is one of the more important points when we start to evaluate each project or each area or reservoir, because let's suppose that we receive from the meter some amount of CO2, and we need to be sure that this amount of CO2 can be stored during the time in the geological formation. Because then, if it's not enough, we need to looking for another formation to back up, or need to looking for another formation, another bigger formation. Yes. This capacity, it's when we're referring also to the porosity, the net thickness, the area, and of course we need to take in consideration here the pressure. The pressure, it's where we refer about the reservoir pressure and fracture pressure. Here it's important to have in any CO2 storage project to have a geomechanics evaluation, because the fracture pressure is really important when we do the CO2 storage project. Then another technical factor, it's related to the injectivity. Injectivity is the amount of CO2 that we can inject into the wellbore, to the formation, yes? This injectivity is in function about our reservoir condition like permeability and net pay, and of course for pressure. Yes, injectivity is not the same. The injectivity, when we talk about the depleted and saline aquifer, there is some difference basically regarding to the fracture pressure and initial reservoir pressure, because, for example, in the case to depleted oil and gas reservoir, we can inject the CO2 until when we reach the initial reservoir pressure. In the case to depleted saline formation, it's we can inject the CO2 until the maximum fracture reservoir pressure. For that reason, it's important to have the geomechanics and fracture pressure in this assessment. Yes, in the case to depleted, it's important to take into consideration the current reservoir pressure in order to mitigate the Joule-Thomson effect. Joule-Thomson effect, it's really can be mitigated with some action like heating in the wellhead or reduce the CO2 rates into the injector wells. Okay. And then another technical factor to take in consideration is the containment. The containment is related to the capacity of the formation to maintain and the CO2 during the time in a secure way. This containment is taking in consideration the seal integrity of the formation, any possible fault reactivation, seismicity, the well integrity, because we need to be sure that the cement into the wells need to have a good cement, or in the legacy wells or existing wells need to have a very good assessment that there is not any pathway to this CO2 move to the another upper formation or to the surface. Yes, this containment also include the monitoring during the time. Where it goes in more detail about the well integrity. Well integrity is really important in the CCS project, basically in the depleted oil and gas reservoir, because as we see it here in the picture, there are several pathways or roads in order to the CO2 can be migrate between the formation to another upper reservoirs or to the surface. Once we have established these technical criteria, then we can have our selection criteria and ranking our several prospects that we have, because when we evaluate any CCS project or geological storage area, sometimes usually we included several prospects. Based on that, we need to ranking and to select which are our best candidate to continue with the evaluation and the project. Here in this slide, I can show the main steps about the CO2 storage project. As we see here, this is the timeline that include the site selection that sometimes we take around 1 year, this assessment. Then the site characterization can be taken around 3 years maximum. Then the storage design and construction can be taken around 5 years. That this will be depend of the project. The injection operation, because this will depend of the contract or the project, can be leased until 40 years. Yeah. Then the site closure will be depend, but maybe can be extend 5 years more or depend of the contract of this process, and then the post closure of the project. Yeah, this is only to reference about how much is the timeline about and the step for CO2 storage project. And then this slide is a summary about the assessment and development process. This is for the International Energy Agency, that we can see that for the different steps for regional screening, site selection, initial characterization, detailed characterization, and design and development. Each how much is the potential sites? If you see interregional screening, maybe we can have 100, but then when we go to site screening can be reduced, and of course with the site selection can be reduced more. And then when we go to the initial characterization, it's a more specific and so on. Yeah. And of course, this is another assessment and development process for CO2 storage or geological storage, but taking consideration the technical factors, the containment, monitorability, injectivity, and capacity estimation, and the ways that we can use for each technical factor. Depend of the information that we have, we can estimate our assessment using some analogs or some analytical method, and then in the way that we have more information, we can use some dynamic model and geological model in order to estimate better our injectivity and plume migration in our project. Mm-hmm. Here it's a summary of these evaluation methods. As I mentioned before, we can use some analogs like in oil and gas, but as we know, there is not so much CO2 storage projects, and based on that, we have some limitation about that. Then we can include some performance analysis, like some injection pressure and injection rates, and do some pressure tracing analysis, like in oil and gas, of course, in order to estimate our injectivity and how much CO2 can be injected into the wellbore, and some production analysis or some similarity like productivity with the injectivity as in oil and gas. And of course, the simulation, it's a very important tool that we need to use before to start injection, and then once we start to injection into the project in order to have a better understanding, a better match for our project. This is part of the information that we need when we start modeling the CO2 storage project. This is pretty similar to the oil and gas. We need all the subsurface information, like reservoir petrophysical properties, relative permeability, porosity, permeability, capillary pressure, wettability, fluid analysis, and etc. It's a process really similar to the oil and gas. Then, regarding to the activities and project life cycle, the European Commission have defined some legal framework about the CO2 storage sites. And when we start the geological CO2 storage, when we can see that in the exploration, there are some points defined by the European Commission, like we need to define the suitability of geology, characterization of the storage, access to storage capacity, and important thing is the injection testing. Yes, it's like a pilot project in order to be sure that the well can be injected amount of CO2 that we receive by the meter. Because here in the CO2 storage project, it's important that we receive some amount of CO2 that we need to respect and we need to inject. Let's suppose 2 tons of CO2 every year. And these 2 tons need to be constant during the year, and we need to be sure that these 2 million tons can be storage every year. Let's suppose if the well cannot be storage, cannot be injected, we need to drill another well in order to can be respect this contract, this agreement that we have with the meters. Yeah. Then when we refer to the storage side, there are some important points that the European Commission defined, like that is important to routine annual inspection and surface and injection facility, and of course the monitor storage. Additionally, the European Commission, they have some key permit and operating obligation about the CO2 storage. Of course, this is by the European Commission, and then each country can be defined an additional specific obligation for each storage project. But this is important to take in consideration because this is our legal framework. Yeah. And this is all from my side. Thank you very much. And if you have any question, comment, please let me know.
Thank you, Sonia. In fact, there were actually several questions in the chat, but we'll probably go ahead with the next presentation. Then we'll try to address all the questions for this presentation and the coming one in the Q&A session after the next presentation, if that's okay. So please, if you have questions for Sonia, please write them down in the chat, or you can keep them, and in 15 minutes, we'll open the floor for Q&A. So now we'll have Callum presenting. I'll pass the floor to you, Callum. Please go ahead.
Hey everyone, can everyone hear me and see my screen?
Yes, Callum, we can see your screen and hear you properly.
Stuff. So hey everyone, it's great to meet you all, and thanks for giving me the opportunity to present. Hopefully you'll be able to understand my Scottish accent, so I'll try to speak clearly. So my name's Callum Barrow, and I'll be presenting an overview of the Northern Endurance Partnership Subsea CO2 Injection System. Some background about me. I graduated from the University of Aberdeen with a Master's in Mechanical Engineering. I'm also a Chartered Engineer with the Institute of Marine Engineering, Science and Technology. I started working for Equinor as recently as May this year, based in Scotland. And prior to this, I was 15 years with Chevron, working in projects, operations and technology development for business units in Europe, Eurasia, West Africa and Australasia. My expertise is in subsea facilities engineering, major capital project execution, and low carbon solutions. Start by talking about Equinor's low carbon solutions ambitions, as well as our portfolio. I'll then talk about the Northern Endurance Partnership and how that fits into the East Coast cluster. I'll briefly provide a high-level overview of the Endurance CO2 store, followed by a detailed overview of the NEP, that's Northern Endurance Partnership Subsea Injection System. In Equinor, we are committed to the goals of the Paris Agreement, and in 2050, we aim to be a net zero company. To enable this, by 2030, we aim to spend 50% of our investments in low carbon solutions and renewables. Within low carbon solutions, our focus is on decarbonising hard to abate sectors of the energy system using CCS, with ambitions to store 15 to 30 million tonnes per annum of CO2 by 2035. We have a long history of storing CO2 both on the Norwegian continental shelf and internationally. In Norway, since 1996, we have stored CO2 at the Sleipner field, and since 2008 at the Snøhvit field. And internationally, since 2004, we have stored CO2 from the Inshallah field in Algeria. Other projects in our portfolio, which are in the design and execution phases, include the Northern Lights and Simihaya projects, both on the Norwegian continental shelf, the Bayou Bend project along the Texas Gulf Coast, and the Northern Endurance Partnership on the UK continental shelf. We're also involved in the development of the CO2 highway pipeline, transporting emissions from mainland Europe to CO2 stores on the Norwegian continental shelf. Right, Right, I'm going to talk about the Northern Endurance Partnership and how that fits into the East Coast Cluster. So in October 2021, the East Coast Cluster was selected as one of 2 clusters within phase 1 of the UK government's cluster sequencing process. Now, what is the East Coast Cluster and how does it relate to the Northern Endurance Partnership? Well, the East Coast Cluster is the overarching term for the full project CCS value chain. The Northern Endurance Partnership will serve the East Coast Cluster as its dedicated CO2 transportation and storage system, with sufficient capacity to transport up to 10 million tonnes per annum from Teesside and 17 million tonnes per annum from Humberside. Equinor, BP and Total Energies are partners responsible for NEP. On the capture side of the value chain, we have emitter projects in Teesside and Humberside. Some of these projects are owned by Equinor. For example, we have a minority share in a post-combustion capture power plant called Net Zero Teesside Power. And we also have a 100% share in a blue hydrogen production plant north of the Humber called H2H Saltend. In March 2023, as part of phase 2 of the UK government's cluster sequencing process, 3 emitter projects were selected to initially connect to the Northern Endurance Partnership TNS system. So when I say TNS, that's transportation and storage. One of which was our very own Net Zero Teesside Power, which we have a minority share in with BP. You can see here in this timeline just how far we've come and how far we have yet to go. I've already talked about the timeline for phase 1 and 2 of the UK government's cluster sequencing process, which stretched from May 2021 through to March 2023, with regards to a final investment decision for NEP, so that's the Northern Endurance Partnership, and the 3 selected emitter projects. This is currently planned for next year, 2024, with an expected date for commercial operations by 2027. I'm going to start by talking about the Endurance Store, which is a deep saline aquifer. If you look at the cross-section on the right, you have your storage site shown by the blue outline, which is part of the Bunter Sandstone Formation, and has a thickness of approximately 250 meters within the spill point. You have the seal, which consists of Triassic to early Jurassic mudstones and evaporites, including wrought clay and wrought halite. And you have the storage complex shown by the green outline, which is the storage site and the seals within the structural maximum spill point. As you can see from the diagram on the left, it's a 4-way closure, approximately 22 by 8 kilometers, with 3 on-structure well penetrations, including the first ever UK CO2 storage appraisal well drilled back 10 years ago in 2013. To give you a sense of the scale of Endurance, there's 26 billion barrels in place above the spill point, where 100 million tonnes of CO2 equates to approximately 3% of the pore volume. For phase 1 of our development, we plan 5 injectors and 1 monitoring well, where we can inject up to 6 million tonnes per annum of CO2. And future phases will enable us to scale up beyond 6 up to potentially 23 million tonnes per annum of CO2. Here's our field layout. Now, before I go into the details, I just want to talk about the boundary limits for NEP. So NEP, or Northern Endurance Partnership, includes the offshore facilities, the Teesside and Humberside landfalls, the Teesside CO2 gathering network onshore, 3 high-pressure compressors in Teesside, each rated for 2 million tonnes per annum. In Humberside, it also includes a booster station and the CO2 gathering network. And going into the details of the field layout, we have 2 28-inch carbon steel pipelines coming from Teesside and Humberside. That's 143 kilometres from Teesside and 101 kilometres from Humberside. CO2 flow from both Teesside and Humberside commingles at the first manifold. Flow is then distributed to 2 injection wells at the first manifold and 3 injection wells at the second manifold. We also have one monitoring well to provide CO2 plume surveillance. Between the first and second manifold, there's a 6-kilometre 28-inch carbon steel pipeline with 2-kilometre 8-inch super duplex pipelines connecting the manifolds to the wells. One thing that stands out most for the subsea facilities is the use of an all-electric subsea control system with power and communications provided via a direct current fibre optic cable coming from Teesside. With all-electric control systems, the benefits compared to standard electrohydraulic control systems are huge. From a CapEx perspective, significant procurement and installation savings can be achieved by using a DC fibre optic cable instead of an electrohydraulic umbilical. And from an OpEx perspective, as well as increased reliability, you're also significantly reducing well startup durations, as you're not having to wait hours on end to charge the control system with hydraulic fluid. The capital investment for CO2 transportation and storage project is significant. Therefore, when you combine this with the relatively low returns, reliable and cost-efficient subsea facilities for CO2 T&S or transportation and storage systems is important to achieve. Before I move on to the next slide, I just want to talk about some of the things we need to consider during installation and pre-commissioning of the NEP subsea system. For installation across the pipe lay route, we need to consider the potential for sand wave migration. These are dune-like features on the seabed, which can range up to 10 meters in height and can frequently change. Therefore, immediately prior to pipe lay, there is a requirement to pre-sweep these sand waves. And during pre-commissioning, there is a requirement to leak test the system using water. If any free water is not removed from the system, then excessive corrosion could occur once CO2 is introduced due to the formation of carbonic acid. Therefore, there are very strict requirements regarding dewatering and drying of the pipelines down to a minus 40 degrees Celsius dew point, which can be very challenging when dealing with over 250 kilometers worth of pipe. One thing that we are very proud on NEP is our potential to be a first-of-a-kind system. The first ever, which connects third-party emitters directly to a CO2 T&S transportation and storage system. And to enable this, we need first-of-a-kind technologies. I've already talked about the all-electric system and the DC fibre optic cable. However, there are other technologies that have yet to be field qualified, such as the downhole safety valve for low-temperature CO2 service. Now, unfortunately, an electrically actuated downhole safety valve for low-temperature CO2 service will not be qualified in time for NEP. Therefore, we are also having to qualify a subsea hydraulic power unit in the absence of an electrohydraulic controls umbilical to provide localized hydraulic power to that downhole safety valve. With regards to the qualification program for this downhole safety valve, this is being coordinated by the Net Zero Technology Centre based in Aberdeen and co-chaired by BP, our partner within NEP, and also Shell. I talked about the low temperature requirements for this valve. In conventional production and injection wells, downhole equipment is generally not subject to temperatures below 0 degrees Celsius. In a CO2 injection well, however, where you have a liquid column of CO2, a sudden depressurization of the well above the valve would cause CO2 to vaporize. This could then send a cold pulse with potential to reach minus 55 degrees Celsius down the tubing to the valve as the CO2 boils off. We're also having to qualify inline intelligent inspection technologies for CO2 service, dense phase CO2 flow metering, and seabed landers for CO2 plume and salinity monitoring. And I'll talk more about this later. However, the way we plan to operate the Northern Endurance Partnership subsea system to account for frequent variation in emitter flow rates, combined with a requirement to operate in dense phase, our choke design needs to be qualified for 20,000 cycles, which is significantly more than what typical subsea chokes are qualified to. Current guidelines like API 6A and 17D require chokes to be qualified to 1,000 cycles under zero differential pressure. Therefore, this gives you an appreciation of the challenge that we have ahead. For future phases of NEP, we may decide to deploy further technologies like the electrically actuated downhole safety valve I mentioned earlier, but also downhole distributed acoustic sensing. On this slide, you can see a CO2 phase diagram and our operating conditions. So subsea will be operating in dense phase conditions, and subsurface will be operating under supercritical conditions. When I talk about dense phase conditions, it just means a fluid which has the viscosity of a gas, but the density of a liquid. I mentioned earlier that our operating philosophy needs to consider frequent variations in flow rate due to dispatchable power and plant outages. Therefore, to maintain the operating pressure above the critical point, as shown within this phase diagram, we need a subsea control system that is designed to accommodate this. Out of the 3 emitters selected for the first phase, we have 2 supplying base load emissions, so constant, and 1 supplying varied emissions due to demand from the grid. So let's walk through this all the way from the emitters through to the wells. So let's say that all 3 emitters are flowing under normal operating conditions, where the pressure at the first manifold that I showed earlier is around about 115 bar. Now let's say net zero T-side power under dispatchable mode is turned down. This reduction in emissions flow rate will likely result in a pressure drop at the first manifold below our operating envelope. Therefore, to counter this, we need to choke back on the wells so that the pressure at the first manifold increases back to 115 bar, and we maintain our operating pressure above the critical point. Some of the wells will be selected as variable, where their chokes will be adjusted to achieve this, and other wells will be selected as fixed. In low flow conditions, where net zero T-side power is turned down and you might have an outage with one of the base load emitters, we also need to consider the risk of 2-phase flow downstream of the choke, which may result in vapor collapse and choke cavitation. We also must consider the impact of adjusting the chokes excessively, which may result in wear to its internals, which is why we need to qualify it to 20,000 cycles. And we also need to ensure that the pipelines aren't pressure cycled excessively, which may result in fatigue damage. Now, if you take all of this into account and consider that the flow to each well must be at sufficient pressure to achieve the desired injection rate, and that we are not exceeding the injection capacity, which may result in formation damage, this drives the need for a very unique subsea control system. And hopefully you can see these graphs on the screen. I appreciate it's very small, but yeah, so we have a strict CO2 entry specification, which all emitters are required to comply with. This entry specification presents allowable CO2 composition with regards to impurities such as water, hydrogen sulfide, NOx, and SOx. For example, we require water content to be less than 50 parts per million, which will ensure that we are always operating outside the hydrate formation curve under steady state and transient conditions. To ensure that we are always flowing with the required CO2 spec, continuous CO2 composition monitoring and sampling by the emitters and NEP, Northern Endurance, will be done to ensure that any excursion is detected. In the event there is any excursion, which may make its way through to the subsea facilities, for example, an increase in water content beyond 50 ppm, then there may be a requirement to dewater using pigs or just use on-spec CO2 to dilute any free water. On the right of this slide, there's a great figure which shows the various categories of excursions. You have a dew point excursion, which can result in liquid dropout, 2-phase flow, vibration, slugging, and subsequent mechanical damage. A bubble point excursion, which can result in the same impacts as a dew point excursion, except you obviously have gas breakout instead of liquid dropout. A fluid corrosion excursion, which can result in the formation of carbonic or sulfuric acid, and a hydrate excursion, which can result in the formation and transportation of solids. The other figure on the slide on the left presents a great picture of how the CO2 phase behavior changes because of a fluid corrosion excursion. The blue line here is the phase envelope for CO2, and the orange line is the phase envelope for CO2 plus 20 parts per million of sulfuric acid. Our subsea operating conditions are around about here, so you can see just how much the phase envelope changes due to this type of excursion. I'd like to finish with some closing comments. I presented here why the design and operation of subsea facilities for CO2 transportation and storage possesses unique challenges which are not typical of standard subsea production systems. For example, a strict CO2 entry spec is required to minimize the risk of two-phase flow, hydrate formation, and corrosion. The requirement to operate in dense phase conditions, combined with the variations in flow rate, pipeline fatigue limits, choke cycling limits, and subsurface injectivity boundaries, result in the need for a very unique subsea control system. And last of all, most of the technologies required to enable reliable and cost-efficient CCS developments are still less than TRL5. So that's at the prototype stage. And to close, I just want to emphasize this message. The Northern Endurance Partnership aims to be a pioneer within the global CCS industry by building the world's first ever CO2 transportation and storage system, connecting industrial emitters directly to a CO2 store. We also aim to be at the forefront of industry for the development of technology required to enable reliable and cost-efficient CO2 transportation and storage systems. Thank you, and any questions?
Thank you, Callum. Thank you for the presentation. We will now open the floor for questions for both presenter, Sonia and Callum in this case. There were some questions that were already in the chat that I can see that Sonia started addressing some of them. I'm not sure if there is a particular would like to address it here, Sonia. If there is a particular question that you'd like to address, or you'd prefer us to go to all of them, it's up to you, because I saw that you answered some already.
Yes, I tried to answer some of these. For example, one of the questions, if it is important to take in consideration the type of rock. And yes, the type of rock is important, because then we need to consider that there are can be some reaction between the CO2 and the mineralogy in the rocks. Then about another question is about economics. Yes, the CCS, we talk about economics because at the end, the CO2 is not a commodity. It's a waste that we need to inject in order to don't have this emission in the atmosphere, no? And it's expensive because this is a process that we need to capture the CO2, the emissions, and then transport, and then will be a storage. And don't pay for that. The problem is it's for that this is economic. It's not the economic is a challenge, you know. And then we need to have the monitoring during all the phases of the project, because it's not only at the beginning. It's during all the time we need to monitoring that the CO2 not migrate to another upper formation or to the surface. That is some challenge, you know. There are some countries like in United States that in ER there are some incentive for funding that help to or promote some CO2 storage project. But yeah, it's a challenge about economics. I don't know if Callum wants to add some about that.
No, nothing more for me to add there, Sonia. Completely aligned with your thoughts there.
Thank you. There was a question. It says probably for Isabella, I think you might have addressed, but the question says, you have a rough estimation of expected worldwide CO2 storage capacity. I'm not sure if it was addressed.
Which question?
It's a question by Lucia, and Lucia was asking if you have a rough estimation of the expected worldwide CO2 storage capacity.
No, I don't have the brief estimation. I know that there are some publication with that estimation, but of course, one important thing is that the amount of CO2 that can be stored, it's larger in saline aquifer compared with the depleted, but the number I don't have in mind. There are some maps that we can find into the web that we can find that which places are the best or to have more amount of capacity to be storage the CO2, but I don't have the number at the moment.
Thank you for your answer. There was also another question for one of the guests. I cannot see the name, but it says hi. Okay, it's from Vincent from Exxon. Thank you very much for the great talk. Got another meeting on endurance. Would it be possible to find the talks afterwards, and are they recorded? I think this was answered by Soraya. Yes, the talks are recorded. Thank you, Soraya, for that. And the questions on the economics was also answered. Why is it mandatory to inject the CO2 in its supercritical phase?
It's not mandatory to inject in supercritical phase. It's not mandatory. You can inject in liquid, inclusive can inject in gas phase. The problem is if you inject in gas phase, you can inject less volumes compared with the liquid or supercritical phase. That's it. But one of the important things is that ideally is to the CO2 can be stored at supercritical condition, because this is the best phase in order to have higher density and less and volume and compressibility. That's it. But it's not mandatory to inject in supercritical. Need to evaluate all the value chain and the pressure and the emitters or capture point, the transport, and then in the wellhead. Because it's possible to put some compressors into the transportation phase. Yeah?
And Sonia, just to add, it's probably, from a subsea facilities perspective, we want to operate in dense phase conditions, minimize occasions where we're in two-phase flow, and that kind of operating philosophy on dense phase, when you account for the hydrostatic head of the CO2 liquid column, kind of drives that kind of supercritical condition subsurface. So yeah, it's not a mandatory requirement.
Yeah.
Thank you. There was also another question for Emilian for both speakers, and it says, imagine a best case scenario 15 years from now for CCUS technology. Which number seems more realistic to you? Capture of 1%, 10%, 50%, or even 100% of our CO2 emissions. So I guess
this question. Emilio refers to direct air capture, or which technology? Because it will be depend. I think so.
So I can provide some context on the East Coast cluster. So I'm talking from a UK perspective. So if you take all of UK's industrial carbon emissions, the East Coast cluster has the potential, I've read, to reduce that by 50% at its maximum capacity.
Okay. There was also another question from Yan, and it says, why do you expect such pressure drop and Joule-Thomson effect in saline aquifer? Is it due to CO2 column pressure at the wellhead? I think this is for you, Callum.
You're mute, Callum.
Yeah, so you're exactly right there. So it is a combination, not just the liquid column of CO2 in the wellhead, but it's also based on the flow rate that's actually upstream of that choke, combined with the setting of the choke itself.
Thank you. That was pretty clear. There was also another question from Olivier, and he asked, did you consider surface facilities for the wells or platforms, or was it not cost effective?
Yeah, so I can answer that for NEP. So yeah, we obviously, our selected concept is subsea facilities tied back to shore. You know, way before my time, you know, I am very confident that fixed unmanned platforms were assessed as an alternative, but a subsea solution was decided as the most cost efficient and cost efficient alternative.
Okay. There was also a question from Roberto, who is sitting next to Luce, and is asking what are the risks or consequences of sabotage or terrorism?
Yeah, I mean, you know, as with all major capital projects, that's something that you have in the very, you know, high consequence, low likelihood range in the risk matrix. You know, it's something that always needs to be considered. In the UK continental shelf, we see very little of that, you know, others much more so. But yeah, it's obviously something that you need to consider. Hopefully I answered your question there.
I think you did. I think you did. There was also probably it was the final question in the chat, and it says, are the offshore CCUS projects has the one presented by Callum in the same range of cost as the oil and gas developments?
Yeah, very similar. You know, if I talk about the capital investment required for the subsea facilities, it's exactly the same as, you know, building a subsea facility for a traditional oil and gas development. Your returns are obviously a lot smaller, and that's why you need to make sure that the system you're building is as cost efficient as possible. And, you know, technologies like direct current fiber optic, all electric control systems, not only being, you know, eventually cheaper, but also a lot more reliable. So you've got a lot more uptime there for your CO2 transportation and storage system.
Thank you. Thank you. Those were all the questions in the chat. But if there is any question that wasn't written here, I think you could just raise your hand or just unmute yourself and ask directly to the speakers today. If anyone has a question, it seems okay. It seems that there are not additional questions, but several messages of people and all of us here thanking all the speakers. In this case, Fernanda, who is no longer here, but also thank you to you, Sonia and Callum, for such wonderful presentations and for answering the questions that were posed here. Thank you very much for this. I'll just take this minute just to remind of the event that we have upcoming, which is it's entitled Navigating Career Challenge and Opportunities of the Energy Transition, and it'll be on the 19th of October. So just keep in touch with us, and you can also follow us in our LinkedIn page, where you'll find more information about our upcoming events. And if you'd like to join us as a chapter, you can also feel free to email us, and this is the email of our chapter. Apart from that, I would like to say thank you to everyone who has contributed to this session, to questions, but also answers that were provided. And this will be the end of our presentation today, and looking forward to meeting you all in our next presentations. Thank you very much, everyone.
Thanks, everyone. Bye.
Thank you. Bye.
Thank you for
Bye.
coming.